Okay, so everyone, probably we can start, right? It's bit too. So, first question: are there any questions about the previous times? I still need to write some problems. Probably I'll do in this today or tomorrow. They will be in the same file. So. Today, I want to tell a little bit more about the Fourier transform on a real line. Like, you remember the last computation we did the last time was the computation of the inverse Fourier transform of identity. So we computed this integral. Was it omega or x? I don't remember. And we found that d omega or 2 pi, we found that it equals to delta function of t. And now, so it was an example. And now I want to prove that in this continuous case, direct and inverse Fourier transformation are actually inverse to each other. So, namely, let us say that there is a function f of t. No, better to say that there is a Fourier transform of a function f, which we denote by f tilde of omega, and it equals to integral over dt e to the 2 pi I omega t f of t from minus infinity to plus infinity. And we want to compute, we want to check the inverse transform of this function. So we want to compute the integral from minus infinity to plus infinity dt e to the minus 2 pi I omega t. Let us maybe write some t prime in the very beginning. F tilde of omega. So first of all, we saw that sometimes it turns out that yes, thank you. Yes. So there is a question like for which functions we can compute on this Fourier transform, and namely we should ask that both f of t and f of t and f tilde of omega are in L1 of R, which means that integrals of absolute value of f of t dt, and the same for its Fourier transform. And they should be defined and convergent. In this case, we see that if this integral is absolutely convergent, then initial integral is also convergent. But So this is what we are asking here, but in reality, in all practical applications, these conditions are not necessary. Because, for example, and there is a perfectly defined Fourier transform of a function uh, e to the so dt e to the some I a t squared over 2 e to the I omega t dt. This is a perfectly defined integral. So we ask these conditions just for convenience, and in reality, if you need to compute a Fourier transform, you ask some proper ways to define it. For example, define it for some complex value of the argument, and then compute analytic continuation, and so on. So this is, for example, in this case. We can add some small regularization to see that this integral is computable. Oh, sorry. So what here? Squared over t. Or we can understand in the other way that this function is oscillating so quickly that contributions at big T cancel each other, we'll actually compute this integral. But for a moment, let us restrict to this case when both function and its Fourier transform are in L1. And if this holds, then we can try to do the following. So let us consider by the way, let us denote it as f with two tildes of t prime. So let us consider the function f tilde of omega f epsilon tilde of omega, which equals to f of f of omega times e to minus epsilon absolute value of omega. And now let us see what is the difference between sorry, this one. And now let us see what is the difference between f two tildes epsilon of omega minus f two tildes of omega. So we can write that it is less than, maybe less or equal to to the integral from minus of t. Sorry, it is less than equal to integral from minus infinity to plus infinity e absolute value of f tilde of omega times 1, maybe I'm better to write this one, 1 minus e to the epsilon absolute value of omega. And now let us say that um, so now let us say that since this absolute value of maybe let's put absolute value here. Absolute value of this integral of this absolute value is convergent, then we can say that there exists such omega epsilon that what is this?
Since 1 minus e to the minus epsilon absolute value of omega is positive and converges pointwise to 0. And the all the whole function in the integral can be majorized with absolute value of f tilde of omega. We can conclude using the theorem of dominated convergence for the Lebesgue integral that the integral goes to 0. Epsilon goes to 0.
So you're saying that we don't need to prove this. We can just refer to this theorem.
If there is inner one, we can do without using the Riemann integral, but just using the integral is faster.
Okay. Thanks. So I can write at this moment that it goes to 0 when epsilon goes to 0, right?
Yes, because pointwise there is convergence to 0, and we have a function that dominates the whole sequence depending on the parameter epsilon. A function that is in L1 and does not depend on epsilon.
Yeah. Thank you. So. Yeah. So I was going to split this integral to the main part, which gathers everything up to some epsilon corrections, and was going to prove that this goes to 0 and the other part also goes to 0. But yes, if you say that we can refer to something and so maybe you can write that it is O of epsilon, right? Something, or just say that it goes to 0. Maybe it's a correct estimation, right?
If you want to get O of epsilon, you have to use the Riemann integral and estimate the convergence to 0. The convergence theorem doesn't give an estimate.
And maybe it's not even true. I'm not sure, but let's just say that it goes to 0. Yeah. Thank you. So now we see that these two integrals go to each other in the limit, and it is and they converge uniformly in T. And now we can compute this integral, namely, let us compute f with two tildes epsilon of t prime. It is a integral from minus infinity to plus infinity, a integral in dt, f of t e to 2 pi I omega t minus t prime, integral d omega dt d omega e to minus epsilon absolute value of omega. And we computed this integral the last time. So here I divided by 2 pi. Sorry. And also there. So it is integral from minus infinity to plus infinity. Dt delta epsilon of t minus t prime f of t. So and I remind that this delta function is epsilon over pi epsilon squared plus t minus t prime squared. So now we can say that again this integral can be split into some parts from, for example, a square root of epsilon, so that this that integral of the delta function is definitely greater than so it tends to 1 when epsilon goes to 0. So we can write that it is integral from maybe not square root, better to say that some epsilon 1/3 to be on the safe side. T0 minus epsilon 1/3 to T0, so T plus epsilon 1/3 dt delta epsilon of t minus t prime f of t plus integral from t prime from t prime plus epsilon 1/3 to infinity. Well, the same integral from minus infinity to this other limit. And now we see that this is of order epsilon 1/3. So this integral will go to 0. And we are left with this integral, and here we can take a limit from. So here we can take a limit, mm, and in the limit this f of t will go to f of t prime. So we can write that it is f of t prime, uh, f of t prime plus integral from prime minus or times integral. Mm, mm. And so no, plus sum all of psilon 1/3, and this integral also goes to 1 in the limit. We can check this by explicit integration of that expression. Mm. So, but it's clear intuitively that this function equals to 1 when t minus t prime is of order. Mm, so let me think of order square root of epsilon, and then it goes. So if go further from 0, it will go to 0, and mm, well, mm, I don't want to compare this explicitly, but it should be uh, mm, understandable, or mm, maybe it's better to show it. Mm. So we want to compute, we want to estimate the integral of this function, epsilon over epsilon squared plus t squared dt, when from epsilon 1/3 to mm, infinity. Uh, So here we can neglect this first term, and it will look like a integral from epsilon 1/3 to infinity epsilon dt over epsilon squared. Oh no, dt over t squared, and this equals to. So this integral is convergent, and it equals to epsilon over epsilon 1/3 equals to epsilon 2/3. So it goes to 0. We can write 1 minus 1 plus O epsilon 2/3. Yeah. And finally, this gives f of t prime, and plus some O of epsilon 1/3. So, and when epsilon goes to 0, we find that f of the 2 tildes of t prime equals to f of t prime. So the Fourier transform is actually inverse to itself. Hmm?
For taking f of t prime out of the integral, we use continuity language or
Yes. So actually, I want to. I was going to say it later. But okay, for a moment we can ask also that this f and f tilde f tilde are in the intersection of L1 functions with uh, I think yeah, continuity should be enough. C0 of R, but I'm going to show that this requirement is actually it will follow automatically from the requirement of requirement that Fourier transform is in L1. So I'm going to show it now because. Mm, So are there any questions about this computation? Mm, mm. Or it's fine? Mm. Oh, what? Uh, uh, we can call this continuity or differentiability. Uh, integrability. Uh, so mm, uh, so suppose that we have uh, a function that has a discontinuity of order um, order R. Uh, and then its Fourier transform behaves as omega to mm, so what I think maybe minus R minus 1 when absolute value of omega goes to infinity. So now how to prove this?
Is this true even for poles in the complex plane? Like if we take f of t to be like 1 divided 1 plus t squared, that's poles not in the real line, but in the
Which?
That's physical.
No. If it is continuous on the real line, then there will be nothing like this. So which example do you want?
1 divided 1 plus t squared.
So let us just compute the Fourier transform of this function. It will actually appear, I think, today or the next time. So it is integral dt e to the e to the I omega t over 1 plus t squared. And now there are two cases. Of course, when when t is greater than 0, we can close this contour in the upper half plane, and this integral equals to uh, to 2 pi I times residue at t goes uh, to I e to the I omega t, t plus I, t minus I. And when t is less than 0, this 2 pi I times residue at t whose minus I the same. Uh, yes, thank you. Thank you. Yes. So it equals to mm, so here we see that we'll get here I, which will cancel this I, or actually 2I. So it equal to pi times e to minus omega t. And here we'll get p times e to the plus omega t. So in total it equals to p oh, pi minus minus omega, yes, okay, e minus omega. So it is a function which goes to 0 faster than any power of t, because this function was continuous. But here we see the opposite phenomenon. If we try to take an inverse Fourier transform, we see that this function decays as t minus 2. And if you look here, this is precisely what is predicted. It has a discontinuity of the first derivative, this function, and so its inverse Fourier image behaves like 1 over t squared. So
you know why this one decays so fast is that 1 over 1 plus t squared is integral is infinity and no discontinuities of any order.
yes. So and this integrability, or the rate of decay of the Fourier images, is translated to continuity properties of initial functions, and vice versa. By the way, what is your name? Thank you. Thank you. Get this. So how to understand this? It can be understood. So if you forget about convergence of integrals, then naive argument is the following: that integral from minus infinity to plus infinity dt f of t maybe okay, to I omega t. We can integrate this by parts, namely let us say that it is integral from minus infinity to plus infinity dt sorry, e to d e to I omega t over I omega times f of t equals, so we should ask that this function goes to 0 at plus and minus infinity, probably, or if it is an L1, then, or we still need this requirement. Again, in any case, ask it and all its derivatives go to 0 and at plus and minus infinities, and then integrate by parts. So we have integral from minus infinity to plus infinity, uh, mm, minus 1 over I omega f of f prime of t e to the I omega t equals equals to, and so on, integral from minus infinity to plus infinity, I over omega to power n f n of t e to the I omega omega t. And once we differentiate it, and so we can differentiate this function until we get delta functions in its derivatives. Like maybe we can stop at the previous stage and divide this integral into parts where this derivative is still continuous, and estimate any of these integrals, but maybe it's easier just to differentiate it until we get delta functions at some point, and then say that it equals to sum over I over omega to power n times omega k, some coefficients ck, times e to I omega k is time t, plus something continuous. So equations.
The computation of those integrals is because the first part of integration by parts annihilates because it's infinity and minus infinity is 0, right?
Yes, probably it's some extra assumption, but I think we can again imagine that even if this function grows faster to infinity, we can regularize it by such kind of exponential, compute this integral, then remove it. So it works in most cases. But
Should be in L1, right?
yes.
So infinity should be 0.
Yes. Yeah.
So, okay.
So so let me think. Okay. No, actually, maybe I might be wrong, but I think I can write a function which is in L1, but is not zero at some points at infinity. For example, if we add uh, if we add some combination of this delta functions, which are more and more narrow, such that their integrals go to zero fast enough, then we still can get a function which is in L1, but there are some points where it is finite. Mm. And, like, ah, yeah, yeah, I was thinking about something more smooth, but yes, so we can. Mm. So probably it's some extra assumption, but I think it can be removed if we add some regularization and prove that everything converges. So mm, here we can say that if this integral is mm, convergent, like nth derivative is continuous and is in L1, then we can say that the Fourier image of this function is less than omega to power n. And if you want to know precise, like more precise asymptotic, we can differentiate it once again and see these contributions. Mm. So, for example, here we see that mm, so let me think. Mm. So here we see, for example, that a discontinuity is at the point zero, and for an image of this function behaves like 1 over t squared, and not like 1 over t squared times some exponential. But if we add here some exponential, make it oscillating at infinity, for example, let us put here e to the I alpha t. Then we'll have here omega plus alpha t, and here we will also have omega plus alpha t. So it will also be here. Which will mean that which will mean that the Fourier transform of this function it behaves like 1 over omega squared times this exponential. So is it fine? Are there any questions? Hmm? Hmm?
These things that we have described by e to the I alpha t, when we have it also to the
Oh, I don't understand. Oh, here I just modified this initial function to see what happens with its Fourier image. It shows this phenomenon that asymptotics of a function which has discontinuity at a point minus alpha will contain such exponential.
Is this not true for a function?
Uh, uh, yes, and this derivation shows that if nth derivative of a function has discontinuities, then mm, has yeah, nth derivative of function has delta functions, so n-1 derivative has discontinuities, then asymptotics of the Fourier image at omega goes to infinity behaves like exponential times 1 over omega to power n. So, and here was an illustration for this function. So, is it fine? So, by the way, what is your name? So, what is your name? Ah, good. Mm, so yeah, this was about this mm, continuous Fourier transform. And concerning the relation between properties of Fourier image uh, and the original function, you remember probably from the last time that there is also this other property that if one function is analytic in the upper half plane, then the other function is zero for negative t's. So there was uh, also this. Mm. So I also want to do the same as we did here for the functions on a circle, but it's not only to have everything improved, but because we will get some formula for delta function on a circle, which can be used to prove so-called Poisson resonation formula for the functions on a real line. So mm, so we obtained the formulas for direct and inverse Fourier transformation, like phi of phi is equal to some uh, fn e to the minus en, or maybe I don't remember the notation, maybe in this one. And formula for these coefficients is that fn equals integral from 0 to pi. So f is from 0, phi is from 0 to 2 pi. Equals integral d phi over 2 pi e to minus I n phi f of phi, yeah, like this. So if you want to prove that these two transformations are inverse to each other, we can do this, for example, from this representation. Let us try to compute the so uh, sorry. Mm, Let me check the recording is on. Yeah, suppose that we have some function which is this sum for integer n's. And try to compute the m's coefficient. So integral from 0 to 2 pi d phi over 2 pi e to the minus 2 minus I m phi sin phi sum for integer n it equals to the integral from 0 to pi d phi over 2 pi yeah. Mm-hmm. So and sum over m sum over n f tilde n. So we can compute this integral from 0 to pi, and what does it equal to? So what does it equal to for n different from m? Yes. Yes. And when n equals to m, it is 1. So we integrate 1 from 0 to 2 pi, and then divide by 2 pi. So it is delta n m. So we compute the sum and we get f tilde m. So we checked in this direction that Fourier transform and the inverse Fourier transform are inverse to each other. But let us try to compute the different composition. Let us suppose that we take we compute a sum over n in z of e to the I n phi times integral from 0 to pi d phi over 2 pi phi prime e to the minus I n phi phi prime f of phi prime. So we now need to compute such a sum, and so here we wanted to check that it equals to f tilde m, and here we need to check that this equals to f of phi. So we need to compute. So if we interchange summation and integration, we have integral from 0 to 2 pi d phi prime over 2 pi, and here it is sum over integer n's e to the I n phi minus phi prime f of phi prime. So here we need to compute the analog of delta function. So in the continuous case, we had this integral over omega t minus t prime, and here we have discrete summation in n e to the I n phi minus phi prime. Uh, So again, this sum is not very well convergent because their absolute values are 1. But here we can do the same trick. We can say that f of phi prime goes to 0 fast enough. So it is in L1 on a circle, and we can add here a regularization. So the following sum will the following expression will converge to this one when epsilon goes to 0. 2 pi. And here is e to the I n phi minus phi prime minus epsilon absolute value of n, f of phi prime. So you can expect what the answer will be. We will compute the sum, prove that it is again a delta function of phi minus phi prime, and then we will get f of phi. But let us compute this delta function. So so it will be 2 pi times delta function. So it is n. Let us write that it is n from 0 to infinity e to the I n phi minus phi prime minus epsilon n plus sum from a different n from n equals to 1 to infinity e to the I n phi prime minus phi minus epsilon n. I changed the sign of n in this other sum. So both of these expressions are geometric progressions, and we get delta epsilon of phi minus phi prime. Oh, sorry. It equals to 1 over 1 minus e to minus epsilon plus I phi minus phi prime plus, so this geometric progression is a little bit different. So it is 1 minus e to minus epsilon minus I phi minus phi prime So we can rewrite this a little bit. Mm, maybe mm, maybe on the other blackboard. This one, for example. So mm, so it is one minus to the maybe better to write like this. No. Oh. Mm, like this, right? Mm, yeah, it seems to be correct. So now look what happens here. When epsilon goes to 0 and phi is different from uh, phi prime, uh, then we have a difference of two equations that coincide. Uh, so uh, So remind that this is delta epsilon of phi minus phi prime. So when phi minus phi prime is not in is not 2 pi times integer, uh, then a limit epsilon goes to 0. Uh, delta epsilon of phi minus phi prime equals to 0. And
Isn't it p first minus p in the second dimension?
yes, because here we had summation over integer numbers, and I change.
The other one.
Hmm?
From there to the next there shouldn't we get
Yeah. So let me think. Yes, thank you. Mm. So, no, but I put minus sign here, so it should be fine. So, is it fine or not? I've changed sign in front of this bracket. Is it okay? Mm, mm, okay, so here we see that epsilon goes to zero. Limit is zero from for phi different from phi prime, and if phi is close to phi prime, uh, or uh, like this. But let us say that it is just around zero. So if phi minus phi prime goes to zero, then the delta epsilon of phi minus phi prime uh, is uh, is of this kind. It is epsilon mm, minus I phi minus phi prime plus 1 over uh, uh, here with yeah like this, and if you combine this together, and we get 2 epsilon over epsilon squared plus I plus phi minus phi squared phi prime squared. So it is 2 pi times delta function of phi minus phi. So in the limit, it goes to a delta function of phi minus phi prime. But if you want to check that its integral is 1, we can just integrate in dphi, and then go to a complex variable and compute the residue in one of these points. So we can check that integral of this function is 1 before taking the limit. But uh, here is an important difference from the delta function on the real line. We see that it is periodic in phi and in phi prime, and in this phenomenon occurs also when phi and phi prime differ by the by some 2 pi times integer. So it means that this delta function is actually this delta epsilon of phi minus phi prime. Uh, maybe it's better to use some special notation for this delta function, delta s1. S1. Uh, S1. So the delta function on a circle is a sum over all integers delta r1 of phi minus phi prime. So other sorry, plus 2 pi n. So are there any questions about this? So so if not, you see, so we prove that it is a delta function. So we prove this original formula that if you take sum of the Fourier components of some function and as the coefficients of the Fourier series, then this Fourier series will cover the function itself. So this is done, but we also get this formula which relates delta function on S1 to delta function on R1. So it's if we consider this phi as some real number, then this delta function will be this infinite kind of comb. So delta S1, and this is phi. Mm-hmm. So I'm telling this because it has some nice application, and this application looks like this. Probably I can erase all this. It's called Poisson estimation formula. So here it's convenient for a while to introduce some other normalization of the Fourier transform because in this case coefficients are easier to remember. So let us say that there is some f of x which equals to integral from minus infinity to plus infinity dk f tilde of k e to the 2 pi I kx, and there is the inverse transform. In this case, coefficients are 1. dx f of e to the minus 2 pi I kx. Uh, then, if we take sum of the values of this function in the integer points, it will magically equal to sum of values of its Fourier transform also in the integer points. And how and it is clear that this formula is useful because what we actually want to do to prove this relation. We need to apply, we need to take this representation as a Fourier series and just take the sum. So proof. Sum over n equals to z go from minus infinity to plus infinity decay f tilde of k e to the 2 pi I k n because x equals to n. So this is a sum of f of n equals to that. Now we compute this sum, and it equals to toward integral from n. So first let's write this integral decay f tilde of k. And here, as we remember, it should equal to 2 pi sum of sum over some other L delta function of the argument here is 2 pi 2 pi k plus 2 2 pi L. And you remember the property of a delta function. The delta function of some function equals to 1 over the derivative of this function times the delta function of points where it equals to 0. So I'm saying basically that we can cancel this 2 pi here and here. There's a simple consequence of that property that delta of ax equals to delta of x. You can check this easily, either from the definition or from the general formula. So maybe it's better to put minus L because it does not matter. And then now compute this integral. It equals to sum over L integer f tilde of L. So the end of proof. It is useful when we try to study modular properties of Jacobi theta functions. And for example, it can be used when we study heat equation on a circle, because there can be two different representations of its Green function, which are related by this Poisson summation formula. Are there any questions? Yes. So, and here phi could also be in R because there was no restriction. It was just some variable defined up to 2 pi. So this delta S1 on a circle has only one point where it is infinite because we identify all of them. But on a line, it's a combination of delta functions in all the same integer or pi integer points.
Probably it's clear, but we took the sum over n inside the integral, and then the sum over n of those e to the 2 pi I in the n is the same as we defined the of the circle, and so we used the last formula, that one.
This one, yes. So, so there is also one question of convergence of this Fourier transform. Maybe it's easier to study it for functions on a circle. So the problem is that if we take a function f which has some discontinuities, then, well, so in all other cases, when f is continuous, this convergence of partial Fourier sums is uniform. But if f has discontinuities, then a typical situation is that nth partial Fourier sum around this discontinuity goes like something oscillating, and the maximal value of this oscillation does not go to zero when we send the the limit of truncation to infinity. So in this case, convergence is not uniform, and it's called a Gibbs phenomenon. But probably I want to talk about this some other time, and today I wanted to tell something about the actual differential equations in several variables. So, so and let us start from the heat equation. Maybe we can what to call a green function of the heat equation. So let us let us study this equation on maybe like this. So at this moment, I want to forget about all those boundary conditions, initial conditions, and so on. And sorry, f of oh, let us just solve it for the green function t minus t t0. Well, everything is uniform, so it's delta of x. Like t is in R, x is in Rn. and mm, the boundary conditions should be specified somehow, boundary conditions and initial conditions, but for a moment let us mm, say that we just try to compute something, and then we will think in more details what are these conditions, what are the assumptions, and so on. So let us try to do something naive, like, sorry, it's equation for the gain function. Uh, how to define this? We put here minus I omega times g tilde. Here we put plus k squared times g tilde equals to 1. So this green function is g tilde is mm, 1 over minus I omega plus, or maybe it's better to write it already. Oh, sorry. I over I over omega plus ik squared. So we obtain this function quite easily, and now we need to compute its Fourier transform. And by the way, we see that this function is not in L1 of this, oh, sorry, if x in some R d in n-dimensional space. So we see that it's this function is not in L1 of R d plus 1. But nevertheless, as long as we can compute its Fourier transform, it is fine. So if we want to, like, so we're looking for a g of t and x. It equals to the integral d omega over 2 pi d k over 2 pi to the power d. I e to the minus I omega plus omega t plus I kx over omega plus ik squared. So, and now let us first compute this integral in omega. We actually computed something like this the last time. It's because on this equation, if you look at this as at a equation for fixed Fourier mode, it is just the same equation as we had. dt plus dtg plus gamma g equals to the delta function. So do I remember the answer for this integral? So this pole is in the lower half plane, So if t is negative, we can close the contour in the upper half plane, and it will be 0. So it is proportional to the delta function, to theta function, to theta of t. And when t is positive, we can close this contour in the lower half plane, and it gives us just residue at omega equals to I k squared. So it is the integral dk or pi to power d e to the I no, so e to the minus t k squared e to the I k x. And that's all. We don't have any denominator. So remember, here we could expect some problems with convergence because this grand function was not in L1. But here, after taking this first integral, the second integral is convergent very well, like, for any positive t and so on. So is it fine? And now, who knows how to compute such integrals? Yes.
And then we have an integral on the Gaussian function, which is another Gaussian, another constant.
Yeah. So yes, it is theta of t integral d dk over pi to power d. Maybe it's not enough space, but let us try. It is a t of k plus no, so probably I should go to the next line. So it's this full square, and we also need to subtract the square of this term. So it is minus x squared over 4t. And now we have these integrals in each component of k. It is No, because when we compute the product of this, we get uh, minus I k x divided by t times 2, because it is 2 in the middle term, and then multiplied by t. So this 2t in this term cancel, and here it appears again. And now, we have a kind of integral. Uh, this is a Gaussian integral over some shifted line. So the function is e to the t in case, for example, kx squared, but integral goes over uh, some r r plus I plus some shift. But it's easy to see that since this function at infinity goes to 0, we can easily add such modification of this integral, and it will be the same. And then we just move it back to the real line. So it's easy. This integral equals just to the integral over over the real line of e to minus t k squared. So it is theta of t, and this integral for each component is the same. So hmm?
and I is missing in the previous integral, the minus I x squared over 40.
No, okay. Here is this term. This term should cancel with what comes from this bracket. Here we have minus I squared. This is one minus. Another minus is here. So here it comes with positive sign, and then it cancels this term.
Okay.
So the point is that this expression, if you open this bracket, will equal to this one. So here we have d times the same integral minus from minus infinity to plus infinity e dk over 2 pi e to the minus t k squared to power d times e to minus x squared over 4t. Theta of t. So this integral without t equals to square root of pi, and if we add t, we should divide by square root of t. So after all, the answer is this: e to minus x squared over 4t divided by 4 pi t to d over 2. So squeeze it, fine. And now actually we can stop at this stage here. And compare with the formula that we had for a discrete equation. So in that case, we have the formula for green function, which was a sum over a finite set of momenta times exponentials, which depended on coordinate, times exponential to t times the eigenvalue of Laplacian acting on this exponential. And we have the same situation here, but this discrete sum is replaced by the integral. So, but now let us try to think about the meaning of this green function. Mm, so we see that it goes to 0 when x goes to infinity, which is fine, which means that we can use more or less any functions as the right-hand side of equation. And also it vanishes for negative times. So it means that if so uh, so we obtain this, and now we ask what are the conditions. Probably I can erase this. What are the conditions which are imposed on the solution of this heat equation? Mm. So we can write formally that there is this heat equation minus Laplacian of u equals to f of x and t, and suppose that this f is 0 for t less than 0. Or we can take arbitrary values in principle. So this u will equal to the integral in dt dx this theta of t minus dt prime dx prime e to minus x squared over 4t minus t prime over the denominator f of x and t prime. So this is that from the properties of this green function, it follows what from this.
X minus x prime squared
Yeah, thank you. f of x prime at prime. Mm.
Also,
Hmm?
for pi t minus t prime.
Ah, yeah, thank you. Mm. Because of this theta function, we can, so it's u of x and t. Because of this theta function, we see that uh, that this mm, u is zero also for negative t's. For t less than 0, and it actually also equals to 0 for x for, well, it equals to 0 for t equals to 0. Somehow it happens that this stupid computation with the Fourier transform of a green function, then computation of the coordinate expression for the green function is a bit clever. So it tells us what is the natural initial value problem to consider. Like, so all these computations were absolutely natural, and we obtained some natural result. So now we can also get the others. We can also get a solution for this problem with some initial condition for you, like how to get initial condition. So we want a solution of a problem that dt u minus Laplacian of u equals to 0, and f of and u of x 0 equals equals to some u0. So there is a simple way to get this. We just say that let us consider uh, uh, the following equation: dt u